This video will serve as a brief introduction to the topics of animation and motion in SOLIDWORKS. To gain more experience in these topics, I suggest you look at the built-in tutorials under the same name. In this video, we'll go over 3 different applications involving animation and motion in SOLIDWORKS. First, in animation, we'll force one part to rotate through an angle dictated by mates. In the second part, we'll utilize physics-based gravity in order to allow the pendulum arm, shown here, to be able to freely swing once given an initial angular position. And then lastly, we'll do what's called a motion analysis, which imports not only the physics, but allows you to track the motion in terms of, for example, angular displacement, velocity, and acceleration. Motion analysis also allows us to import forces and friction. Animation and basic motion are built into the core of SOLIDWORKS. Motion analysis requires you to enable the motion add-in. If you recall, your add-ins can be found at the top. Under Options, you'll find Add-ins. Upon clicking that, SOLIDWORKS will load up the various kinds of add-ins that are available to you. You will need to seek out and activate SOLIDWORKS Motion. Before we begin with our trials in animating and bringing in physics-based motion, let's take a look at the model. It comprises first of a base. The base, you'll note, is not fixed in space, but I've used mates in order to fix its location in space relative to the origin. Then there is the pendulum arm. You'll note that there is a minus sign next to the part labeled pendulum arm in the Feature Manager design tree, indicating that the pendulum arm is free to move. If I were to click on Move Component, I can verify this. Further exploration of the mates will reveal that the motion of the arm is restricted by a concentric mate and a distance mate relative to the pendulum base. In other words, the pendulum arm is fully constrained with the exception of rotation. We can use what's called a position mate in order to temporarily align the pendulum arm in an initial position of our choosing. We can do so by going to Mate, selecting 2 of the features. In this case, I'll select this flat feature on the base and this flat feature on the top of the pendulum arm. Note that by default it has set this to coincident. I'll try to set it to parallel instead. And by scrolling down, you'll note that the very last checkbox under Options reads, Use for positioning only. By clicking this mate will then only be used for positioning, meaning that any changes to the position as shown in the graphics area will be maintained. However, this mate will then be automatically deleted. For example, if I now click OK and enter back into the Feature Manager's design tree, you'll see that under Mates, we do not have an angular mate. If I go back to Mate and reapply the same mate, but do not click for positioning only, the mate does appear. You'll note that when you have that mate, the part can no longer move. I'll delete this mate and leave it as is. The first thing I would like to show you as a new feature is called an exploded view. You can find the exploded view tool under the Assembly tab when you have an assembly open. If you click on the exploded view tool, it will allow you to define a number of explode steps. This involves you selecting the part that you wish to move and the direction in which you want to move it. You'll note that once I've moved it, SOLIDWORKS has created what's called an explode step. If you expand that, you'll note that this part, pendulum arm, has been exploded or moved away from its initial position in the assembly. If we click OK and go to our Configuration Manager, we'll note that we have a new configuration, in this case called the default configuration. Under the default configuration, you will find an exploded view. If you right-click on this exploded view, you can collapse it and explode it again. Or you may animate the collapse or animate the explosion. Further, you can edit the feature by expanding the exploded view, clicking on the explode step, and then right-clicking and going to Edit Feature. Now you can edit the explode step that you previously created. In this case, we can edit the distance with which we explode or disassemble our assembly. I dragged it and ended up getting 13.74 ... inches. I can make this an even 10 inches, for example, and click OK. We can then go forward and collapse our view again. For our first animation, I'm going to recreate the angle mate that exists between the two parts. In this case, I'll be setting the angle between the flat portion on the top of the pendulum arm and the flat portion on the top of the pendulum base. This will create a mate. I'll be creating an angle mate between those two faces. I'll leave the initial angle as 0 degrees, but we'll be changing this angle in our animation. I'll then click OK, noting that the angle mate has been applied now in our Model tab. To create your animation, you'll be going to the Motion Study tab. Upon clicking the Motion Study tab, an animation pane will be brought up, which shows a timeline and a number of keyframes that exist associated with a number of properties built into the model. In the upper left portion of the animation pane, you can choose the type of study. Here you'll find an animation, which allows you to manually move an assembly and record its motion. Basic motion, which allows for a physics-based simulation. And motion analysis, which allows for more complex physics-based motion. First, let's do an animation. The first thing I'll do for our animation is drag the time key point here that's under the assembly file, in this case the pendulum assembly, from 0 seconds to some predetermined time frame. In this case, it's somewhat arbitrary. I'll choose 6 seconds. This means that we're going to create a 6-second animation. The keyframe that exists right below this refers to the orientation and camera view. If you wish to change the orientation or camera view, you would input new time key points or keyframes at various locations, indicating that at each of those keyframes, you will change the view to whatever view is shown in the graphics area when you've created that keyframe. By default, SOLIDWORKS will linearly interpolate between two different changed states. For the case of different camera views, SOLIDWORKS will linearly interpolate between two different camera views by rotating the model about, as we'll see in a moment. You can also change the lighting of the scene, change the appearances of the pendulum or the arm, or you can change any of the mates. If I expand out the mates, You'll note that there are different mates here that exist for all times, as shown by the solid bar. The angle mate is defined with an angle of 0 degrees at 0 seconds. If we wish to change the angle mate in order to rotate the pendulum arm with respect to the pendulum base, we can do so by adding a new keyframe by right-clicking anywhere in the time frame that's associated with angle 2. In this case, I'll right-click at approximately 1 second and place a key. If I double-click this key, I can modify the property, in this case the angle, from 0 degrees to, say, 90 degrees. You'll note now that a solid line appears, in which SOLIDWORKS will start with an angle of 0 degrees and rotate through 90 degrees. I can then place another key point at 2 seconds and further modify, in this case from 90 back down to 0, and perhaps at 4 seconds we'll place another key, double-clicking to modify the angle from 0 to 270 degrees. And then finally one more keyframe at 6 seconds, modifying from 270 degrees back to 0 degrees. You may now click the Calculate button, which calculates the motion study. Let's see what this does. You can play back now after calculating to show the animation from its start. You can also change the playback speed, but we'll keep it at 1 time speed for now. Now let's take a second look at what's happening as we play through this. You'll note that SOLIDWORKS starts the animation with the part at 0 degrees and then rotates it up to 90 degrees after 1 second. It then rotates the part back down to 0 degrees and then rotates to a total angle of 270 degrees before returning back to 0 degrees. Creating your first animation is as simple as that. You can now save the animation as an AVI file, or use the animation wizard to add either rotation of your view or to explode or collapse the assembly. Let's try using the animation wizard. If I click on the animation wizard, we'll have several options existing. We can rotate the model. If you have created an exploded view, as shown several moments ago, you can now explode the model and collapse the model. In this case, I will explode the model and click Next. SOLIDWORKS now asks us to set the amount of time or duration it takes for the explosion to occur. Remember, an explosion is essentially a disassembly of your model. In this case, 1 second seems reasonable. It then asks you at what time do you want to start disassembling the model. In this case, I'll disassemble it at 6 seconds and click Finish. You'll note that an additional second has now been automatically added to our animation file, where the preliminary motion that we just saw occurs in the first 6 seconds, and an explosion animation will occur in the 7th second. If I go back to my animation wizard, I can also add a collapse animation. Keeping it at a duration of 1 second, we can start this at a time point of 7 seconds. This adds the last second to our animation. you'll need to click the Calculate button again in order to recalculate the full animation. You can then play it again from the start. If you wish to delete the final 2 seconds, you can return the keyframe back for the pendulum from 8 seconds down to 6 seconds after you've deleted the new keyframes created by the animation wizard. If you then recalculate, we return back to our original animation. If one were to go back to the animation wizard and add the explode animation with, again, a duration of 1 second, but let's use a starting time that's somewhere already within our model, say at time 2 seconds. And click Finish, and then similarly do a collapse animation with a duration of 1 second, starting at time 4 seconds. Click Finish. We can recalculate the motion study and find out what it does. If we now play this back, you'll note that we have superposed the rotation and the explode and collapse animations. The animation wizard also allows you to rotate the model, which allows you to change the perspective. For example, if you click Next, you can select your axis of rotation and the number of rotations in their rotation sense. You can then set the duration and the starting time as before. For example, for a duration of 3 seconds, starting from time 0, we can click Finish and recalculate. Note now that we have superposed all 3 animations onto the same time frame. Further, note that we had used the animation to rotate about the y-axis. Indeed, we are rotating around the y-axis, as shown here. However, since our initial view was not looking normally upon one of the planes, either xy or zy, the rotation seems a little odd. If I were to double-click the first keyframe at time 0 and change our view from the current view to, say, a back view, which would look directly onto the part like this, and then recalculate our motion study, we note that the second point and the third point, fourth point, fifth point, and sixth point for the rotation animation have not changed. If we now delete these, and recalculate, we get the entirety of the motion from this projected view. One can go back to the animation wizard, rotate the model again about the y-axis for a duration of 3 seconds, starting from time equals 0, and recalculate. You'll note that the animation of the rotate view now looks a bit more normal. You'll note that upon playback, part of the animation goes outside of the screen. If I delete these keyframes associated with the camera view, And now initially zoom out for the first keyframe, placing the view where I want. If I then go back to my animation wizard, rotate the model, in this case about the y-axis, starting at 0 seconds, and again recalculate our model. Not only has the camera view position changed, but so has the zoom. Once you're happy with your animation, you can save it as an AVI file by clicking on the Save button shown in the animation pane. Upon clicking this, you'll have a number of options, including where to save the file, what to name the file, what kind of file type, which by default is an AVI file, and which graphics renderer to use. If you do not have your PhotoView 360 add-in enabled, you will only be able to use the SOLIDWORKS screen. However, with the PhotoView 360 add-in enabled, you'll be able to use the PhotoView 360 renderer, which allows for photorealistic rendering once you've appropriately applied your appearances and your scenes. You can further change the aspect ratio and the image size, as well as the number of frames per second. You can then go forward and click Save, and after some time SOLIDWORKS will have your AVI file ready for you. To quickly recap, we've manually animated the pendulum arm's motion by utilizing an angle mate and adding key points in the timeline for the angle mate that changes its value from 0 to 90, back to 0, and then again through another range to 270 and back to 0. If we scroll through this manually, we note that from the current perspective, the rotation goes between 0 and 90 in a counterclockwise format, using a clockwise format back to 0, counterclockwise again to 270, and then clockwise again back to 0. Unfortunately, at this time, SOLIDWORKS does not provide robust controls for changing the handedness of the rotation, either clockwise or counterclockwise. If you find that SOLIDWORKS is incorrectly rotating relative to the direction that you wish, I suggest trying adding additional keyframes with smaller angular rotations until the nature of the rotation or the handedness is the correct one with respect to what you desire in your animation. Now let's create a physics-based animation. To do so, let's first create a new motion study by going down to the Motion Study tab, right-clicking, and clicking on Create New Motion Study. This will create a blank motion study for us now to work with. We'll change the type of motion study from an animation to a basic motion analysis. As before, I'll drag the keyframe out from 0 seconds to about 6 seconds, which establishes the total time for our animation. Further, I'm going to disable the angle 2 mate by suppressing it. You're going to find that angle mates are incompatible, generally speaking, with physics-based motion. In physics-based motion, we're going to need to define the direction of gravity. To do so, you can click on the green apple that appears here that reads gravity. You can then define either any given line that exists on your graphics area to define the direction of gravity, or you can simply select X, Y, or Z directions if you've properly oriented your assembly with respect to these axes. I've done so I'll click on the Y-axis. You can see that this green arrow shown in the lower right-hand portion of the graphics area indicates the direction of gravity. I'll then click OK. And further, I'm going to change the view at time equals 0 seconds to a projected view from the back side. going to slightly zoom out, and I'm going to right-click the key at 0 seconds. I'm going to replace the key. That will allow for the entire animation to be conducted from the current viewpoint. In addition to gravity, we should also set something called solid body contact. This tells SOLIDWORKS that two solid bodies are in contact with one another, and that they don't fall through one another when conducting physics-based calculations. To do so, select the solid body contact icon located to the left of the gravity icon. It will ask you to select the components that are in solid contact with one another. I'll select everything shown in the graphics area, which brings all of the parts into the selections box, and click OK. If I were now try to calculate our animation in the motion study, nothing would happen. Everything is in equilibrium even in the presence of gravity. In order for the pendulum arm to begin swinging, we're going to have to initially displace it and then allow it to swing under the action of gravity. In order to initially displace it, we're going to use what's called a motor. First, I'm going to isolate the pendulum arm, which means that you will hide everything but the pendulum arm in the graphics area by right-clicking when your cursor is over the pendulum arm in the graphics area and selecting Isolate. Now I'm going to select in the temporary view show the temporary axes. Now I'm ready to select where my motor is going to be placed. When I click on Create a Motor, it asks us first what kind of motor type. In this case, we're going to use a rotary motor. And then we're going to select a component to move and a direction. The direction is going to be the central axis shown here. A directional arrow indicates the direction of the rotation about that axis. The next box says component to move relative to. Now I'm going to select Exit Isolate to show the fixed pendulum base, which is the part that we're going to move relative to. And now selecting the pendulum base, we're ready to define the type of motion that this motor will do for us. Under Motion, you'll have a number of different options. Rather than using the default of constant speed, I'm going to select Distance. When using a rotation motor, distance really refers to an angular distance. So in this case, you must select the angular displacement. I'll select 60 degrees. The first one is the start time. I'll start it at 0 seconds. And the duration is the second one. I'll say is 1 second. I'll then click OK. And note that a motor has been added in the animation tree called Rotary Motor 1. It turns on at 0 seconds and finishes after 1 second. I'm now going to right-click at 1 second in the time frame for the rotary motor and tell it to turn off. Thus, at 0 seconds, the motor is on and will rotate the pendulum arm through a distance of 90 degrees in 1 second, and then turn off. Once the motor is turned off, in the presence of gravity, the arm should be free to swing. If you were to keep the motor on, it would continue to hold the pendulum arm in place against gravity indefinitely until it was turned off. So it's important to remember to turn your motor off at an appropriate time frame. We're now ready to calculate our motion study. We can then play back from the beginning, and we note that in the first second, the arm is rotated through an angle, in this case of 60 degrees, and then released under the action of gravity. It then swings back and forth at an angle of plus and minus 60 degrees from the vertical indefinitely, because we have not added any friction to this study. Let's play it back one more time. It lifts up and releases, and then under the action of gravity moves freely. Basic motion is good for exactly what it sounds like, computing basic motion. It shows you how an assembly can move under the effects of simple forces such as gravity. In order to perform a more complex analysis of motion, we'll need to use the motion analysis tool. I won't need to create a new motion study. I'll simply go and define this as a motion analysis based study, keeping all the other parameters the same. Once I've done so, I'll have access to a few new options. For example, on the right hand side, I now have access to results and plots. If I click on results and plots, we can now create plots that describe to us the motion in detail. Under results, we'll select a category. In this case, let's select displacement / velocity / acceleration. Then it'll ask you to select a subcategory. Let's select angular displacement. The default of magnitude is fine. It will then ask you what is going to be used, either selecting a mate or a simulation element, or 3 points to create your result. In this case, we're going to compute the simple angular displacement of this face, or in other words, the entirety of the pendulum arm. For more complex motions, you may need to be more careful in selecting which features you need to utilize in order to compute a correct angular displacement, velocity, or acceleration. Now, we're going to go ahead and create a new plot, and we're going to plot against time. If I click OK, we'll now have a new folder called Results, under which we find a new plot that plots angular displacement against time. In order for this plot to become populated, we need to recalculate our motion study. If I now do so, the motion study now calculates. It takes a little bit more time when using motion analysis as compared to basic motion. You'll note here is the plot of the angular displacement of the pendulum arm as a function of time. You can see that it oscillates between plus and minus 60 degrees. One can even calculate the period of oscillation if one were to look at the time between successive maxima or minima of the angular displacement. We can create additional plots if we wish by re-clicking on the Results and Plots tab. Selecting again a category, in this case, we'll go through the same steps, but instead of angular displacement, let's look at the angular velocity. We're going to look at the magnitude of the angular velocity rather than any of the components. And again, we'll select the pendulum arm. We could either create a new plot, which has its own separate axes for angular velocity as a function of time, or we can superpose this by clicking on the radio button for Add to Existing Plot, and then selecting the plot that we had just made called Plot 1. I'll then click OK and recalculate our motion study. If I now right-click on the plot and click on Show Plot, we'll now see both plots superposed on the same set of axes. In this case, it's angular displacement, shown in blue, and angular velocity, shown in red. We can repeat this procedure to also show angular acceleration. Motion analysis also allows us to add friction into our analysis. In this case, friction is contained within the solid body contact that we had originally created during the basic motion analysis. If you right-click on the solid body contact and select on Edit Feature, one can incorporate friction, either by manually importing numbers for the friction if known, or by selecting different kinds of materials. The different kinds of materials that are built in include acrylic, dry and wet aluminum, nylon, dry and wet rubber, and dry and wet steel. These are the built-in materials that have friction coefficients defined in SOLIDWORKS. For example, if I were to use dry steel on greasy steel, the friction coefficients will automatically be imported into SOLIDWORKS. If I then click OK, I can recalculate our motion study where our solid body contact now includes friction. If I were now to right-click on our plot and again show the plot, we now see the resultant angular displacement and angular velocity, both as a function of time and again on the same set of axes, in the presence of friction. The motion analysis add-in also gives us access to the creation of springs and the inputs of other forces. For example, in order to add a spring, one can click on the spring icon located immediately adjacent to the motor icon, which allows you to define which kind of spring, either linear or torsional, the location of the spring, as well as the size of the spring. You may need this for your Project 1. Once you're done with your motion analysis, you can save your assembly, which will also automatically include all of your analysis in the file. When you're ready to submit, go up to File, then go down to Pack and Go. Be sure to include simulation results when you're saving it to a zip file. Lastly, there are a number of other options available to you that are accessed using the Option button located on your analysis pane. By clicking on this, we have the motion study properties available in either animations, basic motions, or in motion analysis. The number of frames per second indicates the number of time frames with which SOLIDWORKS solves the physical equations of motion. For 8 frames per second in an animation, SOLIDWORKS will interpolate 8 different times per second. At 16 frames per second in basic motion, SOLIDWORKS will solve the equations of motion 16 times every second. Increasing the number of frames per second will increase not only the smoothness but the accuracy of your calculations, at the expense of the calculation time. Similarly, geometric accuracy and 3D contact resolution can be increased if needed. Using precise contact can sometimes help when small objects need to collide against other small objects. You can similarly change the accuracy of contact if needed. To sum up the basic motion and motion analysis work that we've just performed, we've created a new motion study and disabled our angle mate, which was initially used in the animation to manually define the position and move through a range of motions and record. We then disabled the angle mate in our motion analysis and instead used a motor, in this case a rotary motor, in order to move the part to an initial position. We then turned off the rotary motor in order to allow that part to move freely under the action of gravity. Had we not turned the rotary motor off, it would have held the place in position indefinitely. We defined the direction of gravity, and we defined solid body contact between all of the parts in our assembly, which prevents the parts from falling through one another. Lastly, we created a number of results plots by going to the Results Plots button and selecting the type of result that we wanted to plot, on which entity to measure, and then we created a new plot or added it to an existing plot. You now have all the basic tools that you need to go and start to animate and play with physics-based motion of your assemblies in SOLIDWORKS.